This video is for section 14.2 about the gas laws. The learning goal is to understand how pressure, volume, and temperature of a gas are related. Let's take some notes on that learning goal. Many scientists have studied how the properties of gases affect each other. In this lesson, we'll look at the relationship between the pressure of a gas, the volume of the container that is holding the gas, and the temperature of the gas particles. We'll look at some laws that were developed by different scientists who studied these properties of gases. First, let's look at Boyle's law. Boyle's law states, if the quantity and temperature of a gas remain constant, then the volume and the pressure are inversely related. To be inversely related means that as one of the variables increases, the other variable decreases to compensate. Here's a mathematical formula showing Boyle's law. P1 times V1 equals P2 times V2. P1 represents the initial pressure of a gas. V1 represents the initial volume of the container. P2 represents a new pressure after a change has happened. And V2 represents a new volume after a change has happened. This diagram shows Boyle's law. On the left side is a container, and the red dots are gas particles trapped within the container. Those particles have kinetic energy, they're moving around, and they're striking the sides of the container, exerting pressure. Let's say that that original container has a volume of 1.0 liters, and that when the particles are trapped within that volume, they have a pressure of 100 millimeters of mercury. Now a change happens. The container becomes smaller. The new volume of the container is 0.5 liters. Look what's happened to the pressure. It was doubled. So when the volume has been cut in half, the pressure of the gas in that container doubles. Here's an example problem in which you'll use Boyle's law. A container holds 2 liters of hydrogen gas at a pressure of 150 kilopascals. The container is enlarged to 3 liters. What is the new pressure? When you have a problem about gases and these properties of gases that we're studying in chapter 14, a good problem-solving strategy is to read through the sentence and underline and label the different measurements as you find them. For instance, a container holds 2 liters of hydrogen. We can underline that and say that that's volume number 1. The volume of this original container. As we read further, we see it says a pressure of 150 kilopascals. We can label that pressure number 1. That's the pressure of the gas in the original container. Now let's read farther. The container is enlarged to 3 liters. I'm going to underline that and label that that's volume number 2. That's the new volume of the container after a change was made. Then reading farther, what is the new pressure? The question is asking me to find a new pressure. We can label that P2. Looking at what we've labeled, we notice that it involves P1, V1, P2, and V2. The law that uses those variables is called Boyle's law, and we can write that down. P1, V1 equals P2, V2. On your quizzes, I'm going to require that you write the formula down that you're using to solve a problem involving gases. So get used to having to write down a formula. Now we're going to make substitutions. In place of P1, fill in 150. In place of V1, we can fill in 2. For P2, we're going to leave the variable P2. That was the one that we did not know a number. And for V2, we can fill in 3. At this point, we've created an equation like you see in algebra class. We want to get this variable alone, P2. Next to it, it says times 3. So to solve this equation, we would divide both sides by 3. That's how you make the 3 cancel away so that the variable is by itself. Take a calculator, go 150 times 2, and divide by 3. This will make 100 kilopascals is equal to P2. Notice that I included a label next to the number 100. My variable was a pressure. The other pressure in the problem was in kilopascals, so I knew that P2 should be in kilopascals. Next, let's look at a law called Charles' Law. Here's what it states. If the quantity of particles and the pressure of a gas remain constant, then the volume and the Kelvin temperature are directly related. What it means to say that two variables are directly related is that when one of the variables changes, the other variable changes in the same way. Like if this one doubles, the other one doubles also. Here's the math formula for Charles' Law. V1 is volume number 1. What's the volume you have to begin with? T1 is temperature number 1. And it has to be a temperature in Kelvin. It cannot be Celsius. V2 is volume number 2, and T2 is temperature number 2. Here's a diagram that shows Charles' Law. On the left side, we have a container. The black dots in the container are gas particles. The gas particles are at a particular temperature, which can be read with the thermometer on the side. Now a change happens. The burner flame is turned up stronger so that the temperature of the gas increases. Notice what happened to the volume. With greater kinetic energy from that extra heat, the particles are striking the container more often. When they strike the top of the container, they're going to force this piston upwards, which increases the size of the container. Increasing the temperature increases the volume. Let's take a look at an example problem in which we'll end up using Charles' Law. And let's apply our problem-solving technique of when we read through it, underline all the measurements and label them with their variables. Here we go. A container holds 2 liters of hydrogen gas. 2 liters is a volume. So that's V1, the first volume. Now let's read farther. At a temperature of 340 Kelvin, that's T1, the first temperature. Now a change is going to happen. The container is enlarged to 6 liters. That's V2, our new volume. What is the new temperature? That's T2. The variables that we've identified are V1, T1, V2, T2. We have a law that uses those letters. It's called Charles' Law, and it looks like this. V1 divided by T1 equals V2 divided by T2. Again, you're going to have to write formulas on your quizzes, so you might as well get used to doing it right now. Now let's make our substitutions. In place of V1 is 2. In place of T1 is 340. In place of V2 is 6. And for T2, we're going to leave the variable T2. That's the one that we did not know. Now we need to solve this equation just like you would in algebra class. This has the format of a proportion. One way to solve a proportion is with a technique called cross multiplication. Multiply diagonally. 2 times T2. That makes 2 T2. That's going to be equal to what you get when you multiply diagonally the other direction. 340 times 6. 340 times 6 is 2040. Now what do you do on both sides to get the variable T2 alone? You would need to divide by 2 so that the 2's cross out. And our answer is T2 equals 1020. We were finding a temperature, and the other temperature was in Kelvin, so we know to label this one Kelvin. Charles' Law only works when the temperatures are in Kelvin. So if you ever have a problem and the temperature is given in Celsius, you're going to have to change to Kelvin using the conversion formula from way earlier in the year. Another law that you use for situations involving properties of gases is Gay-Lussac's law. This law states if the quantity and volume of a gas remain constant, then the pressure and the Kelvin temperature are directly related. To be directly related means that however the one variable changes, the other variable changes in the same way. Like if the pressure is times by 5, then the Kelvin temperature would get times by 5 as well. Here's the math formula for Gay-Lussac's law. Let's take a look at this diagram. On the left is a container, and the orange dots are gas particles moving around in the container. Underneath the container, there's a small flame. Let's say that when the temperature is 200 Kelvin, that those particles in the container exert a pressure of 1 atmosphere. Now let's make a change. Let's increase the size of the burner flame so that the temperature changes to 400 Kelvin. That's going to cause the particles to hit the sides of the container more forcefully, increasing the pressure to 2 atmospheres. Let's try an example problem in which we'll use Gay-Lussac's law to solve the problem. And we're going to use our problem-solving technique of labeling as we read. A container holds hydrogen gas at a pressure of 200 kilopascals. That's P1, the first pressure mentioned. And a temperature of 50 degrees Celsius. That's T1, but you cannot have a temperature in Celsius. So we're going to have to do a little bit of work to find T1. Let's do that right here. T1 is equal to 50 plus 273. This was something we learned a lot earlier in the year. To change Celsius into Kelvin, you add 273. The result is 323 Kelvin. So when we're using our math formula later on, and we're going to fill a number in for T1, make sure that we're putting in 323, not 50. Okay, let's go back to that problem and keep reading. The pressure is decreased to 130 kilopascals. That's our second pressure. What is the new temperature? That's going to be T2. All right, pay attention to what variables we labeled. P1, T1, P2, T2. The law that uses those letters is called Gay-Lussac's law, and it looks like this. P1 divided by T1 equals P2 divided by T2. Now let's make substitutions. In place of P1 is the 200. In place of T1, what do we put? 323 Kelvin, not the 50 Celsius. P2 is 130, and T2 is where we have our variable. Now we're going to use our algebra skills to decide how to solve this kind of equation. This has the format of a proportion, so cross multiplication works well. Multiply diagonally, 200 times T2, and that will equal to, and then multiply the other diagonal, 323 times 130. That's 41,990. To get T2 alone, we have to divide both sides by 200. So T2 equals 209.9 Kelvin. We have one more law to investigate, and this is the combined gas law that puts together the ideas from Boyle, Charles, and Gay-Lussac all into one formula. Here it is. Here's an example in which we'll use that formula. A 6-liter container, that's volume number 1, holds hydrogen gas at a pressure of 65 kilopascals. This is P1. And a temperature of 310 Kelvin. That's T1. The pressure is increased to 130 kilopascals. This is our new pressure, P2. And the temperature is increased to 400 Kelvin. So what variable is this? That's T2. Now for the question, what is the new volume? What should we label this? V2. What's our math formula that uses all of these variables? It's called the combined gas law, and it's still on the screen. Let's make our substitutions. In place of P1, fill in 65. In place of V1, fill in 6. In place of T1, fill in 310. Now on the other side of the equals, what do you put in for P2? 130. What about V2? That's the one that you're going to actually leave as a variable, V2. Okay, now under the fraction line, what do we fill in for T2? That's going to be 400. We've created an equation just like you see in your algebra class, and we need to solve it for the variable V2. Well, look what's next to the V2 right now. Under the V2, there's a divide by 400. We know from algebra that we solve equations by doing inverse operations. What is the inverse thing of dividing by 400? We need to times by 400. So I'm going to times the left by 400 and times the right by 400. When you do that, the 400s cross out. What's left next to the V2 now? It's the 130. The 130 is being times to the V2. From algebra class, how do you remove a number that's been multiplied to a variable? You divide by it. So on both sides, we want to divide by the 130. And over here. That makes the 130s cancel away, and the only thing left is V2. On the left side, we have it all set up to type in the calculator. Remember that numbers in the top are multiplied, and numbers that are underneath fraction lines get divided. So type 400 times 65 times 6, divide 130, divide 310. And the result is 3.9. What's the label we need for this if we were finding a volume? It's going to be liters, because the other volume in the problem was in liters. Here are some check for understanding questions. I'll give you some time to work on these, and then we'll discuss the answers. This concludes the video about some of the gas laws used to solve problems involving properties of gases.